Now I introduce multi-armed bandits using Thompson sampling. In multi-armed bandits, agent takes action A, receive a reward R, and take a sequence of action and receive a sequence of reward. The goal is to discover the best actions and receive the highest reward. The challenge is for agent how to balance the exploitation and the exploration. That means when an agent takes action A, receives a reward R. So the agent needs to decide next, continue take action A, receive more reward, or need to try other machine may receive more reward. So suppose P is a probability of receiving reward R by taking action A. Q is expectation of reward over actions A. That means this expected reward is average of the reward, cumulative reward. So the objective is to maximum this cumulative reward. That means for this expected reward, we need to find the action who can make this a maximum. Then we define this action as the optimal action. Using this optimal action, we can find the optimal expected reward. So the goal is to find this optimal action and the optimal reward. Thompson sampling frames the multi-armed bandit problem as the Bayesian theorem problem. A Bayesian problem, that means here we have so many samples. That means we take action A, we receive reward R. And here, this is prior. Prior means at the beginning or at the earlier time, we are not sure this Q value. So we need to try different action, see how can we receive the larger Q. That's like exploration. And once we increase the action or the reward or samples increase, then we have more samples, then we can improve this likelihood. Once we improve this, the likelihood improved, then this posterior is getting better. Getting better, that means this expected reward is concentrated or converted to the optimal expected reward. That's the idea. So the Thompson sampling in these steps. First, we suppose prior, and then we take all the actions, receive the reward, we got this probability, and then we define this expected reward. From the reward, we find the optimal action, and then we find the reward. And then use this reward, we can update the probability distribution. Here we introduce the two cases. One, the reward is a binary distribution. Another is the reward is a continuous distribution. So see how can we using the sampling, use the Thompson samples to update, to use through the Bayesian theory. We find the optimal action and the optimal expected reward. For the binary reward, usually prior Q is a uniform distribution over 0, 1. So we know the probability to receive reward R is increased, expressed in this formulation. If samples the IID, then likelihood posterior, we can express the posterior in this formulation. Here is likelihood, this prior, and this partition function. In this case, we can express this post-theorem as a beta distribution. A beta distribution, that means we have the parameters alpha and beta. Then for each Thompson samples, we can update the alpha and the beta step by step. Finally, we get convergence post-theorem. And then from here, we find the optimal action and the optimal expected reward. For the continuous reward, the prior can be a standard normal distribution, Gaussian distribution. And the probability is of the receiving the reward is in this formulation. We can calculate from this standard distribution. And then we for the samples, so many samples, we can express this post-theorem as the normal distribution. And so we can prove this to this as a normal distribution with the mean rho is here and sigma square is here. So the follow same idea, we use the Thompson samples, step by step, we update this mean and variance. And finally, when the number of samples tends to infinity, we can get a convergence post-theorem. And from here, then we can find out what's the optimal action and the optimal expected reward. For more details, please check with this reference. Thank you. Bye.